Thank you very much for this very nice meeting. To all the organizers, greetings from Leoben, from the Montana University, the Austrian School of Mines. And in fact, I'm going to present a collaboration between our scanning probe microscopy group and the mineralogy group here in Leoben, together with support from Chemnitz University of Technology. In fact, in 2018, my master student Kevin Graco and me, we attended the NSFE meeting in Freiberg. It's in Saxony. I think it was the second last meeting in person. And of course, we visited there the mineral collection. In Leoben, we also have a nice but fine, a small but fine mineral collection. And in fact, Kevin also has his private mineral collection where he found a mineral aggregate that is in fact so that he could strip off with his fingernail some flakes, and this mineral was also magnetic, as you see here, and he could produce flakes that were magnetics that stick to a permanent magnet. And now Alexander Matkovich, my postdoc at that time, came into play. He learned directly from Konstantin Novoselov how to produce graphene or ultra-thin MOS2, and they just prepared from this mineral here, from this unknown mineral, two-dimensional flakes. Just as a motivation, the world of two-dimensional materials is now growing. From 2004 with the first mechanical exfoliation of graphene. We have now also insulators like ultra-thin HBN. We have the black phosphorus family, the 3,4 family like indium selenide, gallium telluride. Of course, we have the transition metal dichalcogenides. We have metallic two-dimensional materials, and we have superconductors. But for quite a long time, there was a lack of I'm fiddling around here. I see also too much of my, now I have it here. There was a lack of two-dimensional magnetic materials. And it took until 2017 that chromium, germanium telluride, and chromium iodide, two-dimensional layers have been prepared, and they showed, in fact, paramagnetic behavior, but only at very low temperatures. Within the last 5 years, there was a hype to search for room temperature two-dimensional ferromagnets. They have been found now, more or less, but only under UHV conditions, not air stable. And here comes our mineral into place. That is a microsection analysis of our mineralogists. And we see a lot of hematite, magnetite, copper pyrite, and calcite. And if you go in these intergrowth sections in the hematite, you sometimes see very small lamellae that are producing flakes that are paramagnetic. And we did first AFM topography measurements. So they were exfoliated, these flakes, and transferred to a silicon oxide layer on the silicon wafer. And we have here, as you see, several 10 nanometer thick flakes, but we can thin them down to really 2 nanometer height, as it is shown here in this section line 2. And in line 1, you see a situation where there is a folding, and from that we can assume that the minimum flake height of these flakes is 1 nanometer. And here is, to make a short a long story short, in summary of our structural analysis, optical microscopy, atomic force microscopy, and Raman, Lucas explained it already. In Raman, we see magnesium, we see silicon, we see OH groups, and we see a very little iron peak that is not shown here in this fingerprint. But from that we deduce, and that is in agreement also with electron probe microanalysis, with wavelength dispersive spectroscopy. We have about 10% of iron here, and that is also indicated by this fingerprint here, that the OH groups, that the OH peak here has a side peak that is due to the iron incorporation. So also selected area electron diffraction and TEM point to talc. We have talc, what is usually an phyllosilicate containing of magnesium embedded in OH, so with an octahedral configuration, and then embedded in SiO4 tetraeders. These SiO4 tetraeders makes a material air stable. And now there is about 10% of iron replaced, or 10% of magnesium replaced by iron. So from the hematite-rich region, iron interdiffuses. And so we have here really an iron-rich talc, and DFT calculations show that the spin state is quite robust with 3.6 μ. And just to let you know, talc is the softest mineral that we know, that is Mohs hardness 1, and in fact Friedrich Mohs was a professor at Graz University Technology, just 50 kilometers from here. Here are a summary of the magnetic characterization by SQUID, and the black line is here a non-iron or very little iron containing reference sample, also from an area here nearby in Leoben. But we see a clear, in the raw data, a clear but small hysteresis. That is here in plane data. We see it also out of plane at room temperature. So we see an indication of weak ferromagnetic behavior at room temperature. Now we use magnetic force microscopy. We are using cobalt chromium coated probes, and we use either these probes without an external field or an external magnetic field applied in out of plane direction, where we, by using neodymium iron bore permanent magnets, could here add about 300 millitesla external field. And there is a clear magnetic force microscopy signal even for the thinnest flakes. And we see a layer-dependent MFM signal at 300 millitesla here for out of plane. So you see already the monolayer shows a weak but clear magnetic response, and that increases up to 4 layers, and then it stays more or less constant. And we measured now the magnetic response in the 2-pass technique as a function of the lift height. And you can clearly see that with increasing lift height, we have a decrease of the response. Here the black curve is the unmagnetized probe with more or less no response. And here we see now that we can match the MFM signal with the SQUID signal. So we have an 1/z dependence of the magnetic signal by assuming that we have a disc-like magnetic sample and a conical probe. Then we really find this 1/z behavior, and we see, or we can by simple calculation estimate that the AFM probes that we use are inducing about 30 millitesla. Here you see that even after 2 years under ambient conditions, this material still shows this behavior, so weak ferromagnetic response. Just here to show that we have a real MFM contrast. We use EFM, electrostatic force microscopy probes, and we do not see a contrast. Also with an unmagnetized AFM probe, we do not see a contrast, but switching back and forth to MFM probes, we clearly see a contrast, so we can rule out electrostatic charging. Yeah, with that, I would like to summarize here. We have single layer iron type flakes, 1 nanometer thick, that can be extracted by mechanical exfoliation from iron-rich phyllosilicates. So in this case, iron talc. And as revealed by in-field MFM and SQUID, the two-dimensional flakes with about 10% of magnesium substituted by iron exhibit weak ferromagnetism at room temperature. We also did scanning transmission electron microscopy that shows that the iron tends to cluster to a few nanometer large clusters. In contrast to 2D magnets reported until now, these iron talc layers are really stable in air, and we suggest that phyllosilicates, overlooked so far during the search for 2D magnetism, are a promising platform for air-stable magnetic monolayers. And just if you have a last question, where does this particular sample that we used for the production of these flakes comes from? There is an indication. Our sample looks very similar in a optical micrograph like the sample here that has been found in northern Sweden in the Siljan ring. That is a meteorite impact crater, the largest one in Europe, 375 million years ago, responsible for the dinosaur extinct, perhaps. So maybe our samples are a gift from outer space. Thank you very much.